So in this video we're going to talk about gas pressure and how it relates to boiling point. So gas pressure is defined by the force exerted by a gas per unit surface area on an object. So we know that gases, when they are in a container, they're all bouncing around this container and they have a lot of energy and they're striking the surface of the container, and that's what causes gas pressure. So it's due to two things: both the force of the collisions between the particles and the number of collisions that happen. So as gas bounces around, if we heat it up, it gets more energy and it's going to strike the container with more force and more frequently. So the gas pressure increases as temperature increases. Now, a vacuum is when there are no particles present. So there is no pressure because there's no collisions and there are no particles present. So that's what a vacuum is. So it's sort of the opposite idea. If there is a gas present, then there is some sort of gas pressure being experienced. So we just talked about gas as if it was within a container, but we have to remember that we are, existing within our atmosphere that is made up of air molecules and gas. So the pressure that we experience and all objects on the Earth in our atmosphere experience is atmospheric pressure. So it is the collision of air molecules with objects. Now, as we go higher up in elevation, air thins out and there's less gas present, and therefore the atmospheric pressure decreases. Now, the instrument that we have for measuring atmospheric pressure is a barometer. So we just mentioned that atmospheric pressure is affected by altitude, but it can also be affected by weather and temperature. So we know that if we heat up a gas, the gas is going to move more, so that can increase pressure. If there is moisture in the air, that can increase pressure because it adds more gas vapor into the air. So a barometer will measure the atmospheric pressure at any time or in any location based on both weather and altitude. So the unit we use for measuring pressure, the SI unit, is a Pascal. PA. But we also have other units of pressure that are older units, and all of these are on the front of your reference tables. So atmospheric pressure at sea level, or the normal, we call it the normal atmospheric pressure in pascals, is 101.3 kilopascals. And don't worry about memorizing that. That's just on the front of your reference tables if you want to take a look. But we also have two older units, millimeters of mercury and atmospheres. So atmospheres makes a lot of sense. You at sea level you have one Earth atmosphere above you, and so it is one atmosphere. But millimeters of mercury is a little bit weird, and it's actually based on this old school mercury barometer. So how this barometer worked was you had mercury in this open sort of cup here, and then you had a vacuum tube here. And so this is the atmosphere out here where it's black. If it pushed in, so the atmospheric pressure pushed on the mercury, it would cause the mercury to rise up the tube. If the atmospheric pressure decreased, then it would fall down the tube. And so we could measure pressure based on how high the mercury was in this tube, and so it had a little scale of millimeters. And we said that the standard pressure, or 1 atmosphere, or 101.3 kilopascals, was equal to 760 millimeters of mercury in this tube. And again, that number is on your reference tables. Alright, so now we're going to start talking about phase changes and how gases in particular affect boiling point or the vaporization. So just remember that vaporization is when we go from a liquid to a gas. And we have evaporation where that can happen, but we also have boiling, and they are different, so we're going to make a distinction. So evaporation is when at the surface of a liquid, the molecules become high enough energy so that they can escape and become a gas. So if you put a cup of water out on the sidewalk, the sun would hit the water and the molecules at the surface would absorb energy from the sun, and then they would get enough energy that they would bounce out and they would become a gas. So when evaporation happens, it's actually a cooling process, because remember that the temperature of a substance is equal to or proportional to the average kinetic energy of all the molecules in that substance. So if you are heating up the surface molecules and they're gaining energy, but then they escape and leave, then your highest energy molecules are leaving, and it therefore lowers the kinetic energy or the average kinetic energy of all the molecules that are in that liquid. So it's a cooling process, and this is essentially how sweating works. When you get liquid on your skin, that liquid absorbs energy from your body, and then it evaporates off, and that leaves you cooler. Alright, so vapor pressure is the idea of the force of a gas above a liquid. So we've already mentioned vapor pressure back when we talked about water, and the fact that one of water's special properties is that it has a very low vapor pressure. It does not require a very strong force for water to stay a liquid at room temperature. So when we're talking about anything that is open, an open container, then vapor pressure is equal to atmospheric pressure. It's the atmosphere above. However, we can create cases with closed containers where we have a higher vapor pressure above a liquid. So if we close a container and we heat up that container, there will be a gas in there, and that gas, again, remember, is going to start moving more because if we add heat energy, the molecules are going to bounce around more, causing more gas pressure, because gas pressure is the frequency and the force in which the collisions occur, and therefore we can add more pressure or more vapor pressure in a closed container. So this relates to boiling point. So we talked about evaporation being surface molecules. Think of boiling point more as throughout the entire liquid, the liquid has achieved a temperature or has the kinetic energy where the molecules can overcome vapor pressure and escape into the atmosphere and become a gas. The normal boiling point or the normal boiling temperature is the boiling point of any liquid at a pressure of 101.3 kilopascals or standard pressure, and that's also 1 atmosphere and 760 millimeters of mercury. And every substance has a different boiling point. Commonly, we talk about water having we know it has a boiling point of 100 degrees Celsius. Now, vapor pressure is the force of a gas above a liquid. So essentially think of vapor pressure as a gas pushing down on a liquid, trying to keep it a liquid, preventing the molecules in that liquid from escaping and becoming a gas. So when we go higher up in elevation, like to Denver, we know that the atmospheric pressure is less, and therefore the vapor pressure is less. So therefore it takes less energy for the water to become a gas, so the boiling point is lowered. If you look at some of your cake mixes or brownie mixes or anything you're baking at home, you can see that there's typically alternate baking instructions if you're at a higher altitude as a result of this boiling point difference due to the atmospheric pressure. Now, another thing in the kitchen that we use in terms of vapor pressure is a pressure cooker. So a pressure cooker is essentially a pot that's sealed on top, and you put meat and broth into a pressure cooker, and as you heat it, the gas pressure builds up in there, and because there's so much vapor pressure in that closed container, it keeps the liquid in there a liquid and keeps it from boiling. And therefore, we can get the liquid very hot, and it cooks meat very quickly. So a pressure cooker is another example of us using vapor pressure to affect boiling points. So if we just look at this example, you can see that here we've got at sea level, we've got standard pressure, we're at 70 degrees. There is not enough energy throughout this liquid in order for it to boil. If we bring it up to 100 degrees, now all of a sudden we've got enough energy throughout this container in order for the molecules to overcome this atmospheric vapor pressure, and it starts to boil at the normal boiling point temperature. However, if we go to Mount Everest, Now you can see the vapor pressure is a lot less. It's about a third. It's 34 kilopascals. And therefore the temperature to boil is a lot lower. So hopefully this video helps you to understand a little bit more about gas pressure and boiling points and how it affects boiling points.